So if VR represents a vector in the plane of these two vectors, a vector in the row space, a vector in this plane, okay? Any point in this plane, take this one out here, vector from the origin out to this point, it's going to be a linear combination of this vector. We move along this vector until we're at the right point, and then we move in the direction of this vector, and we get to that point. So this red arrow here represents VR, a vector in the plane that constitutes our row space. And Vn is going to be a vector in our null space. So Vn is going to be a vector parallel to this vector, a vector along the yellow line. So we take a VR vector and we take a vector along the yellow line and we add them, and then we see what happens when we apply A. Well, actually what happens is very simple. First of all, A times VR plus Vn we've verified is A times VR plus A times Vn. That is, A operates as a linear operator on the sum of two vectors. Just, okay, if you multiply A by sum of two vectors, you get A times the first vector plus A times the second vector. But Vn is in our null space, and how did we get our null space? By solving the equation Ax equals 0. So Vn is in the null space, okay? It's going to be of this form, okay? A negative 1/3 t, comma, negative 1/2 t, comma, t. Going to be a multiple of this. So A is going to map it to 0, meaning that our total result of A times VR plus Vn is just A times VR. And that's kind of important. Okay. Now, we moved on to another exercise where we said that, okay, we got a matrix A that reduces to this. And then I asked everybody to actually apply some row operations to this to see if you can make it less clear that the matrix reduces to this. Okay? So you get an A matrix. Apply your own row operations. And then we're going to talk about that next.